In this video, we're going to explore what a matrix representation is. By definition, a matrix representation is if we take a linear transformation from U into V, where B is the basis for U of size n and C is the basis of V of size m. And then the matrix representation relative B and C is the matrix in which the first column is the transformation of U with a linear transformation in reference to the basis C. And the second column would be the U2, which is the second vector in the basis of B, the linear transformation and in reference to C, and then all the way up to the however many entries we have on the basis. So it will have, your matrix here will have as many columns as you have bases in B, and it'll have as many entries as you have vectors, or the vector entries for M. So let's go through an example. Now, our first example, we're going to use the standard basis. We're going from polynomials of degree 2 into polynomials of degree 1 over R2. This is how we define that linear transformation. This is how we define the function. It says if I take the leading coefficient, which is A, the linear coefficient, which is B, and the constant, which is C, so this is standard for a quadratic, then the way I'm going to transform that, the function I'm going to do to it is I'm going to take these input values, and then the output would be 2 times A plus C minus 3B, and it would be the multiplication by X, that would be the coefficient on X, after the transformation, and then the constant would be C plus 4B plus 3A. So first thing we're going to do is find the T of U. So the transformation of each one of the basis vectors of B. So what that means is I'm going to put in to my vector, or into my transformation, I'm going to put in x squared. So this is the same thing as T, 1x squared plus 0x plus 0, so that I can get it to be similar to this. And what will come out is 2 times A, which is 1, minus plus C, which is 0, minus 3 times 0, which is B, and we multiply that by X. And then the second piece of the transformation is I'm going to put in C as being 0, plus 4 multiplied by 0, so that doesn't do anything, and then plus 3 multiplied by my A, which is 1. So you can see what ends up coming out is 2x plus 3, which is this. That's where that came from. Now, because of the fact that is over the basis vector for C, and the C is the standard basis, I don't have to do anything. This directly relates, this 2 directly relates to the 2 in that vector, and this 3 directly relates to the 3 in that part of the vector. So then my linear transformation can be described as this matrix, where here is my T of U sub 1, here is my T of U sub 2, and here is my T of U sub 3, and it's going to be with respect to C. Well, because my C is the standard basis, I was able to do it directly. I don't have to do any extra steps. My next example, we're going to have to do some extra steps. So then if I want to evaluate what 2x squared minus 4x plus 1 would be, I'm going to put that in reference to my basis vector in B. So I'm looking at the basis vector B. Well, the first position is the x squared coefficient, the next position is the x, and then the last one is the constant. So there, again, there's no work I have to be doing. So then if I take the linear transformation of my input, which is 2x squared minus 4x plus 1, I can do it as a direct substitution as I did here, or I can do it as my matrix representation of the linear transformation, which we know from up above is 2, negative 3, 1, and then 3, 4, 1. I multiply it by the representation of what I'm putting in my B basis, and then I end up with this, which we know then, because we're now landing in the v, or in other words, I'd be looking at it in reference to the c basis, then I get this answer, which is exactly as what I would have had if I would have just put it in. Now, let's redo this exact example where I have a different basis. It is not the standard basis for polynomials, and so my u sub 1 is this, my u sub 2 is this, and my u sub 3 is this. So these are non-standard vectors for my basis in polynomials of degree 2. And then my c basis is, this is v sub 1 and this is v sub 2. So the first thing I'm going to do is, like before, is I'm going to go ahead and put in the into my linear transformation each one of my u1, u2, u3. So I put in u1, and that's x squared plus 0x minus 2. And then I know it is going to be equal to 2 times a, which is 1. And then it's going to be plus c, so plus a negative 2. Then minus 3 multiplied by 0. And this is going to give me multiplied by x, so that's just that part of it. And then plus, my c is negative 2, plus 4 times 0, and then plus 3 times my a, which is 1. Now, what ends up happening is that this ends up becoming 0 times x, and then plus 1, and that's how come I end up with a 1 right here. Now I have to put this with respect to c. I didn't have to do this on my previous example because my c basis was the standard basis. So now I have to put this with respect to c. So then my 1, which is what I got when I put in x squared minus 2 in the linear transformation, 1 kicked out. Now I have to reference this in terms of the basis, where I have my v1 and my v2. So I know that that output of 1 is going to be some linear combination of my v1 and my v2, so I'm going to call it alpha 1 and alpha 2. That gives me this matrix, where in this case I'm going to put my constants in the first position and then my coefficient on x in the second position. So this represents 2x plus 1, this represents the 5x plus 3, and then of course this references the 0x plus 1. Now I'm going to go ahead and reduce row echelon this, and I end up with this. So that tells me my alpha sub 1 is negative 5, my alpha sub 2 is equal to 2. So the matrix representation of this linear transformation with respect to the basis c is that. So that is my vector representation of when I put in x squared minus 2, I get 1 out, but the representation of that with respect to the basis c, which is non-standard, is at negative 5, 2. And I'm going to repeat that for each one of my u sub 1, u sub 2, and u sub 3. These are all of the vector representations of those linear transformations of my basis. So then I end up with this. So I have this. Now, unlike my previous example, I had my 2x squared minus 4x plus 1. That, when I was able to do a vector representation of that over my b vector, my b basis, because my basis was the standard basis, I didn't have to do this extra step. This extra step is, how do I get from each one of these elements, each one of these u1, u2, and u3, what kind of linear combination am I going to have where I have a coefficient a, b, and c, so that I'm going to end up with this value? Because remember, u1 to 3 are the spanning set, so I'm going to figure out how do I represent this input, which is 2x squared minus 4x plus 1. How am I going to represent that as a linear combination of my basis, u1 to u3? So then I end up with, here's my u1, here's my u2, here's my u3. Here is the coefficients on the 2x squared minus 4x plus 1. I do a row reduced echelon form, and this is my A, B, and C, and that is the vector representation of my input, which is this, with respect to b. Now, once I have that with respect to b, then it's just a matter of multiplying by my matrix, which I found up here, and that vector representation of my input, and I end up with this. So then that is the multipliers, my coefficients, on the linear combination of my V1 and V2. So you can see I take that 96, multiply it by V1, multiply that by a V2, and I end up with the exact same answer as I did before, but with a separate basis. I have a different basis for U and a different basis for V, but I still end up with the same answer. Standard basis, if you get a choice, is much easier to do, but sometimes you don't get a choice, so you can still get there. Okay, so then we're going to look at this fundamental theorem of matrix representation. It says, suppose that this linear transformation, B is a basis for U, C is a basis for V, and my matrix representation is M of the transformation from B with respect to C. I'm going from B to C. That's B first going to C. Then for any element in U, so any value in U, doesn't have to be the basis values, for any vector in U, then I can just do the what I just did, which is the matrix transformation, and then I do my row, and do my vector representation of U over B, or I can find the vector representation of C, find the inverse of that, and then multiply it by my matrix representation and then my vector representation over B. What does that tell us? Well, that tells us that there is more than one way to get to my answer, which is this is what I want. Is I can first do, here's my element U, I can do the linear transformation directly, or I can do the linear transformation by first doing what U would look like with the basis B, find the matrix representation of that linear transformation from B into C, go ahead and do the multiplication of that matrix representation, and then what U would be in reference to my basis B. That would give me the exact same thing as if I would have just done my linear transformation and then put it in reference to my C. So, what does that tell us? That means that we can go directly across, or we can go in a roundabout way. And if we can go directly across or a roundabout way, then I can, of course, use the fact that I can do inverses of my, my vector representation, and I can get in the same place. So now let's take a look at another example. In this example, I have these bases, and you can see right out of the gate that these are non-standard. Here's my B1, B2, B3, and V1, U1, U2, U3, and U4. So I have 4, so here's U1, U2, U3, and U4. And then this would be my V1, my V2, my V3, and my V4. Now we know that the dimensions are the same, and we assume that they're linearly independent, and I could determine if they were or not by doing a quick check, but we're assuming that they are because they're telling me it's the basis. At this point, we assume that it is. This is how we're going to define the transformation, is that we're going to take the coefficients off each one of the x's all the way up to the third, and then a constant. And to put in the 1, 1 position, I'm going to do 3a plus 7b minus 2c minus 5d. And that's what's going to go in the 1, 1 position. So I'm taking polynomials of degree 3 or less and do a linear transformation that's going to put them into matrices of 2 by 2. Here's how I find my first position, my second position, my third position, and my fourth position, if you will. So what we want to do is show that I could go directly like I did before, or I can do the inverse here. So let's go ahead and find the matrix representation. So to do that, I have to start with the vector representation of each one of my u sub 1's over my row of C. So I do my linear transformation, and I put in, this is my that is, how to define that? That was just my A, yep. So A, B, C, and D, and the way the 20 came about was the fact that I took my 3 times my A, which is 1, plus 7 times my B, which is 2, minus 2 times my C, which is 1, and then minus 5 times my D, which is negative 1. When I get done, I got negative 20. And it's the same thing when I did the 45, the negative 24, and the 69. So that's the output when I do the linear transformation of my basis vector U1. However, I want the the vector representation of that. And so to find the vector representation, remember what I have to do is these are my bases for my C. So you can see that this is V1, V2, V3, and V4. And I have my alpha 1, 2, 3, and 4. And then, of course, it's equal to what the output was, but now I have to get it in reference to my basis C. And so this first column gives us the first column in the matrix representation. Now I would do the same thing to get the second, the third, and the fourth column. Just like I did before, I would find the transformation of U sub 2, and with respect to C, that would be that one. I would do this one, which is the transformation of U sub 3 with respect to C, and then my last one would be the transformation of U sub 4 with respect to C. All right, so now that I've done all that, I do then need to find what my input P of X would look like with respect to B. So I'm going to do that before I do the linear transformation. So here's what I have as my P of X. And this is what was given to me, and all I did was rewrite it so that the order was matching the U1, the U2, the U3, and the U4. And as before, this is the coefficients on all of my A's, and that is my constant. Here is the coefficient on X's, and that is the coefficient on X here. Here is the coefficient on X squared and the coefficient on X cubed, where that is the X from here, or the coefficient on the X squared, and this is the coefficient on X to the third. Then what I do is I do the reduced row echelon form, and these are my multipliers for my linear combination. So how I get this is a linear combination of 48 times U sub 1, negative 20 times U sub 2, negative 1 times U sub 3, and negative 13 times U sub 4. If I do those linear combinations, I will get my P of X. All right, so now we've done all of this so that we can use this theorem. This theorem says, let's go ahead and figure out what my row of B of my input would be, and that's this. Then if I multiply that vector representation of my input, P of X, over my B basis, if I multiply it by the vector representation of my linear combination, those two combined are going to give me this answer right here. Now, if I find that those numbers, all I have to do then is take those numbers and multiply them by my V sub 1, V sub 2, V sub 3, and V sub 4. When I do that, I end up with this matrix. So that's where I am at that point. There's my matrix. Now, if I did the direct substitution, in this case, would be so much easier, but I wanted to show you what it looks like to do the transformation from one linear transformation and the basis into another basis. If I did the exact just inputting by the way I define my linear transformation, then there I have it. So why would I want to do this if I could just do a direct substitution? Well, here's the thing. Once you've got it down to this point, then it's just a matter of finding this for each one of your inputs. And if it's just a matter of finding each one of your inputs, that is much easier once you've found your matrix representation, is find the vector representation of your input over the B basis, the basis for U, and then just multiplying all of those by the basis of C than it is to do the substitution. Just is a little bit easier. There are some important outcomes that come out of this, which is if I have U and V, or linear transformation T from U into V, and S is also into U and V, and B is the basis for U in either one, and C is the basis for V for both of them, then I can do the matrix representation as the matrix representation of each one individually first, and then add them together, or I can add the two linear combinations together and then find the matrix representation. So that's kind of nice. More often than not, this is more helpful than it is in this form here. If we have this linear transformation and this alpha belongs to C, so the alpha is coming from C, and B is a basis for U, and C is a basis of V, so I have an element, a scalar multiplier coming from C, then the scalar multiplier of my linear transformation can be determined by doing the matrix transformation as we normally do the matrix representation of the transformation and multiplying that answer by the scalar. So there's going to be times in which that's going to be helpful as well. Now here's our composition, so that if I have this linear transformation from T, which goes from U to V, and S goes from V to W, B is a basis of U, C is a basis of V, no surprises there, and D is a basis of W, then this is the surprise. That the matrix representation of this composition can be wrote as the matrix representation of S on the left and the matrix representation of T on the right. So what that gives us is that basically linear combinations is just a matrix multiplication. So that's kind of cool. So now let's take a look at these two linear transformations, and I'm going to have my first one where I have S, which is going to go from C2 into P2, so entries in the complex plane, and then it's going to be some polynomial of degree 2 or less. And then I'm going to take my second one, which is my P2 into M2, so I'm going to do a, so I'm going to be doing a composition. So this is how I defined my linear combination, or my linear transformation from T, from C2 into P2 is this. Once it's in this form, then the linear combination of S, or the linear transformation of S, is going to be defined in this manner. So then we have these bases where I have my basis for B. Here's my basis for B. Here's my basis for C. And here's my basis for D. So I'm going to do the matrix representation. So the first thing I'm going to do is find the matrix representation of T, of the T first, right? So when I do the linear combination for T, A of B, this is what I get. Now when I do that combination, so now I'm going to do the S of this output, so it's now the input in my outer function, then I end up with this, which cleans up to this. So now I'm going to do the matrix representation of this, and I'm going to start with what it looks like with T. So here's T. T is 3 and 1. That's my first U1, U2. And it would look like over C, it would be the 28 times the 1 plus 2x plus x squared. And I'm using the linear combination, how I define the linear combination. And I'm going to get the 28, 28, and negative 9. So those are those numbers. Then I'm going to do my second basis, my U2, which gives me this. So my first matrix representation of the linear transformation of T from B onto C is this. Now I'm going to do my second one. So I'm going to put my V sub 1 into, so here's V sub 1. I'm going to put my V sub 1 into my linear transformation, and I get this. And as before, I'm going to then find these multipliers, just like I did in my previous example, and find those multipliers. And then I end up with this matrix, or this vector. That's the vector representation of V1, which is out of C onto D. And then I'm going to do that for each one of my V2, my V3, and then I'm going to end up with this matrix. So what this matrix representation is the linear transformation from V into W. So I'm taking it from my basis C onto D. So then the matrix representation of all of this, all combined, would be this. Or in other words, I can find the linear transformation matrix representation. So this is your matrix representation of the one we first found. This is the one that we just found, and I end up with the exact same answer as if I would have done it in a composition up above. So there are going to be times where you're definitely going to want to do each one individually because it's easier, and then just multiply them. Just make sure that the inner function matrix representation is on the right and the outer function matrix representation is on the left. And more often than not, you're going to find that it's got to be that way for the dimensions to match. But I want to say that as a cautionary tale, if your dimensions match in your matrices, that you could put them in the wrong order. So the first one you get done is on the right. The second one you get done is on the left. Some other things that we get out of this is the null space and the kernel. Suppose that T is a linear transformation from U and V, and B is a basis for U of size n, and C is a basis for V. Then the kernel of T is isomorphic to the null space of the matrix representation. This means we can find the kernel of a linear transformation by finding the matrix representation of the linear transformation and then finding the null space of that matrix. And of course, we would expect the null space to be trivial, but not always. The next thing that we get is the range in the column space isomorphism. Suppose T is a linear combination, or is a linear transformation. B is a basis of U, C is a basis for V, then the kernel of T is isomorphic to the null space. Nope, that is not what I wanted to have, so that is not the theorem, because that's just exactly what was up above. That is not the theorem. What the theorem basically states is the row space of T, or the range of T, is equal to the column space of your matrix representation. So that's what should have been in there. So once you find the basis of the range of a linear transformation by finding the matrix representation, and then you'll find the column space for the matrix representation. So that's kind of cool. So let's explore this diagram, which is below, and what the dashed lines are going to represent is the subspace relationship, where there, of course, is potentially a smaller vector space, because subspaces, if they're proper subspaces, they will be a smaller space, but they could be inclusive, so it could not necessarily be the exact same, so be aware of that. Anyways, what this does, this shows us that when we are looking at some linear transformation from U into V, what I can do is take the vector representation of each one of my bases and write it in C of n, which then gives me my matrix representation. I take my vector representation of C and it's going to be in C sub n, and I'm going to end up starting with C sub n and ending in C sub m. Sometimes they're the same, sometimes they're not. The kernel shakes out, and then the null space, a kernel and null space has that relationship. The range of T and the column space of the vector or the matrix representation also has some relationships. So we're almost done here. I know this is a long section, a long video. Suppose that T is a linear combination, B is a basis for C, is a basis for V, T is an invertible linear transformation, if and only if the matrix representation of T relative to B and C is invertible. That means if that is invertible, if T is invertible, then my matrix representation is invertible. So that's kind of nice. So let's find my inverse of my linear combination. We assume it's going to exist to start with. So let's assume it exists to start with. So this is my linear transformation from R, and I'm going from polynomials of degree 3 into a matrix that is a 2 by 2. So we're getting pretty standard on what they would look like, some sort of addition and subtraction of each one of the coefficients and the constant for each one of the positions, so nothing surprising there. Since we are not known what the basis is, let's choose a basis, and let's choose the standard basis because we know that's so much easier, right? So here's my standard basis. My standard basis for my polynomials of degree 3 are 1x, x squared, and x cubed, and then of size 2, the 1 just changes position and 0 everywhere else. So when I put in 1 into my linear transformation, this kicks out. I then do that in reference to C, just like I did on the other ones, and I get this vector. I do x, so I put x in my linear transformation. This is a polynomial that kicks out. These are the linear combinations, alpha 1 through alpha 4, that when I do this, and this is real easy, I don't have to do much work, right? Because this 1 gives me this 1, which is here. The only way I can get a 3 here is if there was a 3 here, which is a 3 here, and etc. So these are really nice because I chose a standard basis, so I don't have to do a lot of work, right? So then I get my other ones. So what I end up with is this matrix. Here's my matrix. Here is the matrix representation of the linear transformation from B onto C. Here it is in all of its glory. Now, from my previous theorem, it says if I invert my matrix representation, it is undoing the linear combination. So that's kind of nice. So I invert this. So I invert my matrix representation. So then, say I've got some matrix, A, B, C, and D. I want to know what it would have been. Would have been the constant, the coefficient on x, the coefficient on x squared, the coefficient on x3. So in other words, I am undoing it. I have the matrix. I want to know what would have been the input to give me that matrix A, B, C, and D. So what I know is my A, B, C, and D over my standard basis for C would be this vector representation. If I multiply that by the inverse of my matrix representation of R, I get this, which gives me this, which tells me what I had to have started out with for my input would have been this value for my constant, this value for my coefficient on x, this value for my coefficient on x squared, and this value for my coefficient on x cubed, which is kind of nice. Now, what that now tells me is that suppose A is a square matrix of size n, and we're going from Cn to Cn, the linear transformation, then A is an invertible matrix if and only if T is a linear, invertible linear transformation, which means here is our last and final run at what it means to be non-singular. All of these are equivalent. So A is non-singular, the row reduces to the identity matrix, the null space of A contains only the 0 vector, the linear system has a unique solution, the columns of A are linearly independent, it is invertible. The column space of A is Cn, The columns of A are the basis for Cn. The rank is the number of vectors we have as the basis. The nullity of A is 0. The determinant of A must be non-zero. That lambda is equal to 0, so our eigenvalue is not ever going to be 0. And the linear transformation is invertible. The linear transformation defined from Cn to Cn is defined by this matrix A, which is a matrix representation of the linear transformation, and it must be invertible. So that's it for this section.